The region enclosed by the curves y equals x cubed and x squared is rotated about the line y equals 3. Find the volume of the resulting solid. So up till now we've been rotating around the x-axis and y-axis, and the radius has either been y or x, right? When you start rotating off the axis, so y equals 3 is a horizontal line, of course, it's going to create a radius based on the x or the y, in addition to the distance you are away from the x or y axis. So it's a little bit more creative in finding the radius. That's the only difference here. As far as the beginning part, y equals x squared and x cubed and y equals x squared is the same as it was. If I have to graph y equals 3, I've got to be careful in picking my interval for y. Because if I go to 0.25 scale, 1, 2, 3 is right here, and then all of a sudden I'm going to have to go up above the ceiling almost to get on here. So the y scale, even if the numbers are small, I might have to be a little creative and might be picking my scale. I do, again, want to get it as small as I can within reason. The x-axis on this one is not as bad because I can probably go 0.25 scale on the x-axis. We've already established when we did these same two functions yesterday, 0, 0 to 1, 1 is where they live, right? So if I start off with that knowledge, let me go to 0.25 scale on the x-axis. I'm going to go to 0.5 scale on the y-axis. So 0.51, 0.52, 0.53. And then imagine rotating around that 4 or 5, it'll probably go up to 6. So that's kind of where I'm going to be, and that'll fit within reason on my paper. That's the one thing that's challenging about these sometimes is fitting them on your paper. If I go back to the equations, y equals x squared and x cubed, which don't have them in there anymore, x cubed and x squared, I can get coordinates. So 0, 0.25, 0.5, 0.75, and 1. So if I plot y equals x cubed, which I believe I did in blue, yep, y equals x cubed blue, so 0, 0, and then I got 0.25, 0.02, which is almost 0, and then 0.125, which is 1/4 of the way to 0.5, and then I've got 0.42188, which is almost 0.5, and then I've got 1. So that would be y equals x cubed. And then y equals x squared, I've got 0, 0. I've got 0.25, 0.0625, which is slightly above that. Then I got 0.25, slightly above that. 0.5625, slightly above that. So I create that. Well, that's not very good. There we go. So we have that little sliver there. That's my original region. And as before, I do want to shade that region in. I always want my original region shaded in so I can really establish where I'm starting from. Now the rotation is around the line y equals 3, so if I were to graph y equals 3, that's just a horizontal line at a height of 3, so 0.51, 0.52, 0.53. This is my axis of rotation. So if I rotate that around that, this thing is going to come up here to reflect above it, right? So from 0 to 3 is 3 spaces, so it reflects 3 spaces up. So my reflection should be about like that. And then if I were to draw some ovals or some ellipses here to kind of give it that three-dimensional look, that's what it looks like three-dimensionally. And what I really want to focus on here is if I did a circular cross-section, so I just chopped right down the middle here. Let's get it at one of the fatter parts. That circle right there is the outside circle. And this is the inside circle at the same place. All right, there's my circular cross section. That's what I need to really concern myself with as far as radii is concerned in order to find the area of the circular cross section. So what I have is an outside radius in blue, an inside radius in red. They're concentric circles. And the area that we're looking at is the in-between of the two circles. Like so. Now, again, the radii are where we get a little creative. The original region is here, right? Looking at the blue circle, I know for a fact that this distance here is y. From the x-axis to the curve is y, which you can see very clearly is nowhere, it's not inside the circle, right? Okay, and it might seem like, why do we want to care about that because it's not inside the circle? But here's what we have to do in order to find the radius of these things. We have to consider the outside piece, which has to do with the function, because that's how the radius is changing, right? We have to worry about the actual radius, which is right here. The radius goes from the axis of rotation to the actual edge of the curve. That's the actual radius. And then we're looking for some relationship between those two things that is always going to be true. So as this circle slides left and right, r gets, if I go that way, right, r is going to get bigger, y is going to get smaller, right? But r and y together are always going to be the same distance apart, right? If we take a look from here to here is 3 spaces. So the radius added to whatever y is always going to be 3. So looking just at the blue one, I know the radius plus y sub 1, if this is y sub 1, is equal to 3. Again, I'm just focusing on the blue circle right now. The blue circle is created by the x cubed function. That's the outside function here. Again, I know that because I graphed it already. And I know that y cubed made this bottom one, right? So y sub 1 plus this radius is equal to 3. That means the radius is equal to 3 minus y sub 1. As we've already learned in the first 4 examples in this section, if my circles are moving in a horizontal position, right? So if the circle's vertically positioned but they're moving left and right, I want a dx integral. So I want my radius in terms of x. So I know the radius is 3 minus y sub 1. Y sub 1 is x cubed, so the blue radius is going to be 3 minus x cubed. Using the same logic, if I look at the red radius, so now I'm going from here to here, now I'm looking at y sub 2, right? We're looking at the inside radius that was created by my x squared function. This radius here is still going to be from here to that curve, and they're still going to add up to 3. So the same relationship exists for that. R plus y2 also equals 3. Once you establish this to be true, it's going to be the same truth for the other one, it's just a different function. Which means that r is equal to 3 minus y sub 2. And again, I want this in terms of x, and y sub 2 is equal to x squared, so the inside radius is 3 minus x squared. So when you're rotating off the x-axis, off the y-axis, you're going to get radii that are going to be a some number plus or minus the letter, or the letter plus or minus a number, one or the other. And sometimes you might just have the number itself. Maybe the radius is 2, or in this case maybe it's 3. All right, so if it never changes, it's going to be whatever that number is. Once you've established what the radii are, then it's just a matter of doing the area formula for each circle. So the outside circle is going to be pi times its radius squared. The inside is going to be minus pi times its radius squared. Do be cautious that the radii are binomial squared. You have to square the binomial properly. Also, you're creating multiple terms here that are being subtracted, so you have to distribute a negative through there. So there's a little bit of algebra to deal with here that we're going to have to be cautious with. But if I focus on this one first, 3 minus x cubed squared is going to be 9 minus 6x cubed plus x to the 6th. 3 minus x squared is going to be 9 minus 6x squared plus x to the fourth. Squaring a binomial is what it always has been. Square the first, double the product, square the second. When you square a power, you multiply the powers. X cubed squared is x to the 6th, not x to the 9th. All right? So just simple little housekeeping things from algebra that we may or may not have remembered are going to be happening here. I'm distributing pi through each one of these. So I'm going to get 9 pi minus 6 pi x cubed plus pi x to the 6th minus 9 pi plus 6 pi x squared minus pi x to the 4th. 9 pi minus 9 pi cancels. That may or may not happen. You know, more often than not, these are going to be the same numbers, so if the same number happens, yeah, of course they're going to subtract and make it the same 10 every time, but there's no guarantee that you're going to get that constant to go away. All the rest of the powers don't match up at all, do they? 3, 6, 2, and 4. So my answer is going to be, volume is going to be the pi times the integral of all the x stuff, which is going to be, I'm going to go x to the 6th minus x to the 4th minus 6x cubed plus 6x squared dx. I like descending order, so I'm going to go descending order. Highest power x to the 6th, then x to the 4th, then x cubed, then x squared. Every one of those had a pi attached to it. I put the pi out in front so I don't have to worry about putting a pi on every single term. And these circles that we're taking, this shaded region here, is starting at x equals 0 and sliding all the way to x equals 1. That's the places where the region exists. So our beginning point is 0, our ending point is 1. And then we simply have to integrate, evaluate in order to get the answer. So the volume is going to equal pi times x to the 7th over 7 minus x to the 5th over 5 minus 6x to the 4th over 4 plus 6x cubed over 3. Reduces, reduces. So 6x cubed over 3 becomes 2x cubed. 6x to the 4th over 4 becomes 3x to the 4th over 2. And then we simply have to get a common denominator. The denominators are 7, 5, and 2, so 70. Oh, you know what? Let me substitute the numbers first. That'll be nicer. Okay, so if I put 1 in, I'm just going to get 1/7, 1/5, 3 halves, and 2/3, right? If I put 0 in, I'm going to get a bunch of zeros. So I'm going to get pi times 1/7 minus 1/5 minus 3 halves plus 2/3. If I get a common denominator is 210, sorry, not 70. Oh, it's plus 2, never mind. Plus 2. Now it's 70 again, all right. I wasn't forceful enough in my crossing out of things over here. All right. So put in 1, you get 1/7, 1/5, that's 3 times 1 over 2, and that's 2 times 1, so plus 2. Common denominator is 70. So I'm going to get, again it's pi, right, times all this stuff. I'm going to get 10/70ths minus 14/70ths minus, it would be times 35 is 105, and then plus 140. So 140 minus 105 is 35, minus 14 is 29, plus 10 is 39. Cubic units. That doesn't look right. .104, 140 minus 105 is 35, minus 14 is 21, plus 10 is 31. There we go. I knew that didn't sound right. 31 pi over 7. Helps to subtract correctly. We go full page on this so you can see everything here. So, main idea, the picture is important. If you haven't figured that out yet on these, picture is important. It's important to the extent that you need to be able to determine what the radius is. So draw the picture as well as you need to draw it in order to establish that radius. And on these problems, the radius is not going to be x or y, it's going to be some version of the radius and y equaling a number, or the radius and the number equaling a y, or y and a number equaling the radius, depending on the structure of the object. Short and short make long is basically what's happening there. Sometimes the radius is the long piece, sometimes the number is the long piece, sometimes x or y is the long piece. So it's up to you to determine what that is each time.